Before we jump into things today, I must explicitly state at the very beginning of this broadcast that this audio is actually an AI-generated analysis.
Right. Yeah, good to get that disclaimer out of the way.
Exactly. But with that said, welcome to this detailed technical review and comprehensive analysis of the book, Computer Architecture, From the Stone Age to the Quantum Age by Charles Fox.
It's a fantastic book.
It really is. And we're going to be approaching this material as two expert technical analysts taking you on a continuous chapter-by-chapter journey. We'll start with fundamental physical concepts, move up into the electronic hierarchy, look at some real-world example architectures, and then, finish off by looking at some wild future computing paradigms.
Yeah, and it's essential to begin with the theoretical foundation. Before we even look at the physical hardware, the source material introduces this foundational concept known as the church computer.
Right, named after Alonzo Church.
Exactly, and this concept dictates that a computer is fundamentally a universal machine. Like, if a machine is provided with sufficient memory and enough time, it can simulate the functions of literally any other machine.
And the book has this playful standard for it, right?
Yeah. It playfully establishes a practical test for a church computer, asking whether the hardware can be programmed to play the arcade game Space Invaders.
I love that. Space Invaders as the ultimate benchmark.
Mhm.
But to achieve that universality, a computer has to represent the infinite variables of our physical world as standardized data.
Right, and electronic systems do this using a base 2 numerical system, which we know is binary. And it's not out of some, mathematical preference, but due to strict physical constraints.
Because it's literally just switches.
Exactly. A physical switch is either conducting energy or it is not. It's either on or off, representing a 1 or a 0. But because reading long strings of ones and zeros is highly inefficient for human engineers, we organize these digits using a base 16 system known as hexadecimal.
Which just compresses that data into a more manageable format for human analysis, right?
Yeah, it just makes the code readable for us so we don't go crazy looking at millions of ones and zeros.
So that theoretical universality requires a physical mechanism, which means we actually need to look back at a Victorian mechanical blueprint.
Oh, Charles Babbage.
Right, Charles Babbage's analytical engine. Even though it was designed over a century before the first silicon chip, it possesses the exact functional architecture of a modern central processing unit, or CPU.
It's pretty wild to think about. Gears and steam doing the work of silicon.
Yeah, and it relies on four distinct components. First, there's an arithmetic logic unit, or ALU, to perform mathematical calculations. Second, it utilizes registers to hold the immediate temporary data being actively processed.
Yeah.
Third, it contains a control unit to manage the proper sequence of operations. And finally, it uses random access memory, or RAM, to store larger data sets and, pending instructions. Plus, there's a communication pathway called a bus that connects all of these individual components.
And we can clarify the relationship between these components by applying them to a physical workspace. Like, consider the arithmetic logic unit as a calculator sitting on a desk.
Okay, I can picture that.
Then the registers serve as a small scratch pad located immediately next to that calculator for, writing down quick temporary numbers.
Right, the stuff you're working on right this second.
Exactly. And the random access memory operates like a large filing cabinet situated all the way across the room. Finally, the bus functions as a physical conveyor belt that transports documents between the filing cabinet and the desk.
That is a brilliant analogy. But mechanical gears are inherently limited by friction and physical mass. To process data at scale, architects had to trade moving brass parts for moving electrons.
Which leads us directly to the physics of silicon semiconductors.
Right, but the quantum physics of silicon can be kind of difficult to visualize.
Yeah.
The source actually simplifies this beautifully by considering water flowing through a closed pipe.
Oh, the valve analogy. Yeah.
Yeah. Imagine a mechanical valve controlling the flow of water. When you physically turn the valve, water flows through the main channel. When you close it, the flow stops completely.
That is a precise analogy for understanding modern transistors. In an electronic system, a transistor acts as that controlling valve, and electrical current replaces the water.
Okay.
So, by applying a very small electrical charge to the gate of the transistor.
Which is like turning the handle on the valve.
Exactly. We open the pathway and allow a much larger electrical current to flow through the main channel. When we remove that small charge, the pathway closes.
Oh, you have a switch.
A microscopic switch. And by connecting these individual electronic valves together in specific patterns, we create standard circuits called logic gates.
Like AND, or in NAND gates, right?
Right. For example, an AND gate functions like two valves placed sequentially in the same pipe, so both valves must be open for the water to pass through. By wiring thousands of these logic gates together, we build complex digital logic networks capable of performing Boolean arithmetic.
But um, individual gates alone can't really perform meaningful computation, can they? They had to be structurally organized.
Yeah, they're useless on their own. We organize these networks into two distinct categories: combinatorial logic and sequential logic.
Okay, combinatorial logic links gates to perform immediate calculations, right?
Yeah.
Like an adder circuit which combines binary numbers. That's a pure combinatorial system.
Correct. But computation requires memory. Like, we must be able to store the results of that addition. And this is achieved through sequential logic.
How does that work physically?
By taking the output of a logic gate and feeding it directly back into its own input, we create a continuous electrical loop. This feedback loop forms a simple circuit known as a flip-flop.
Oh, I've heard of those.
Yeah, a flip-flop can maintain a steady state of either a 1 or a 0 indefinitely, provided it has power. This loop is the actual physical foundation of computer memory.
Wow. And when we combine those combinatorial adder circuits with the sequential memory circuits, we can construct a functional control unit, which brings our analysis to one of the earliest digital computers, the Manchester Baby.
The Manchester Baby. Yeah, its control unit is historically significant because it successfully executed the fundamental process that drives all modern computing, which is the fetch, decode, execute cycle.
Break that down for us.
Sure. The control unit fetches an instruction from memory. Then it decodes that instruction to determine which specific circuits must be activated, and then it simply executes the mathematical or logical operation.
The Manchester Baby proved the concept, but I mean, its processing speed was incredibly slow. Modern systems achieve billions of cycles per second.
Yeah, the jump in speed is staggering.
And they achieve these high speeds through advanced architectural modifications, specifically instruction-level parallelism.
Yeah.
One major technique is pipelining, right?
Right. Instead of waiting for an entire instruction to finish before starting the next one, the processor divides the instruction into discrete stages. It functions exactly like an assembly line in a factory.
So while one instruction is being executed, the next instruction is simultaneously being decoded and a third is being fetched.
Exactly. It keeps every part of the processor busy at all times. And in addition to pipelining, modern processors utilize out-of-order execution.
Ah, oui.
Yes. Often, a specific instruction must wait because the data it requires hasn't arrived from memory yet. But instead of halting the entire pipeline and wasting valuable clock cycles, the processor analyzes the upcoming instructions.
Looks ahead.
It looks ahead, identifies independent tasks that don't rely on that missing data, and executes them immediately, completely out of their original programmed sequence. It then reorders the final results before presenting them, which, maximizes the utilization of the processor's resources.
Which introduces a really significant architectural conflict. As the CPU becomes exponentially faster, it inevitably outpaces the speed of the main system memory. There's a fundamental trade-off in hardware design here.
The memory wall.
Right. Fast memory is incredibly expensive and physically small, whereas cheap memory is very slow and physically large. So if the processor operates at these blinding speeds, how does the architecture prevent it from just constantly waiting for slow data retrieval?
Well, architects resolve this bottleneck by implementing a strict memory hierarchy. The processor relies heavily on caches. Caches are highly expensive, microscopic banks of extremely fast memory built directly into the silicon of the processor chip itself.
But because they're so small, the processor has to be smart about what it puts in there.
Exactly. The effectiveness of caching relies on two distinct behavioral principles of software: temporal locality and spatial locality.
Okay, temporal locality observes that if a specific piece of data is accessed by a program, it's highly probable that the exact same data will be accessed again very soon.
Like a loop variable.
Right. And spatial locality observes that if a piece of data is accessed, the data located physically adjacent to it in the main memory will likely be required next.
Like reading through an array of numbers. Based on those principles, the system transfers data from the slow main memory into the fast cache in grouped blocks, which are called cache lines. This allows the processor to manipulate the data at maximum speed.
And what happens if the processor changes that data?
Good question. If the processor alters the data while it's in the cache, it activates a specialized hardware flag known as a dirty bit.
A dirty bit.
Yeah. This dirty bit signals to the system that the cache line now contains a newer, updated value that differs from the original data sitting back in the main memory. Eventually, that dirty cache line has to be written back to the slow memory to ensure system accuracy.
That makes perfect sense. But we also have to address how the processor interacts with external devices,
Yeah.
like keyboards or storage drives. Early computer architectures utilized a method called polling, right?
Yeah, polling was highly inefficient. The processor was required to constantly halt its calculations and ask every connected device, "Do you have new data? Do you have new data?"
Like a kid in the backseat asking, are we there yet?
Exactly like that. Modern architectures, thankfully, utilize hardware interrupts. The processor ignores the external devices entirely until a device sends a specific electrical signal, an interrupt demanding immediate attention.
Much better.
And furthermore, systems now employ direct memory access, or DMA. This technology allows external devices to read and write information straight into the main memory without involving the CPU at all.
So it frees the processor to just continue its calculations uninterrupted.
But precisely.
Okay, so we've established the mechanics of the electronic hierarchy. Now we must examine how these foundational concepts translate into tangible machines. Let's look back to the computing golden age of the 1980s.
Oh, great era.
All right, this era produced highly influential chips, specifically the 8-bit MOS 6502 processor, which drove the Commodore 64 and the 16-bit Motorola 68000. And programmers of this era operated very closely with the hardware. They wrote in bare metal assembly language, directly manipulating the physical registers and memory addresses without the mediation of complex operating systems.
And you know, that direct bare metal methodology didn't disappear. It transitioned into the embedded systems we rely on today. Modern microcontrollers, such as the ATmega 328 utilized in Arduino platforms, operate on identical principles.
So a microcontroller is basically an entire system compressed onto a single chip.
Yeah, it contains a low-power central processing unit, integrated memory, and an input-output interfaces all in one package. Unlike a desktop computer, which must run thousands of unpredictable applications, an embedded system within, say, a washing machine or an automotive engine sensor runs one single compiled program in an infinite loop.
They're engineered for absolute reliability and minimal power consumption.
Exactly.
But while embedded architectures remain lean and purpose-built, the desktop computing market adopted a radically different philosophy. Which brings us to the architectural divergence between complex instruction set computing, CISC, and reduced instruction set computing, RISC.
Oh, the great debate.
Right. The x86 architecture that dominates desktop computing is a CISC design, and the book compares CISC to a massive, complicated Swiss Army knife. It contains a highly specialized, complex hardware instruction for every rare scenario imaginable.
Right.
Conversely, RISC architecture functions like a perfectly balanced surgical scalpel. It is optimized exclusively for the 10% of basic instructions that perform 90% of the actual computation.
And that comparison accurately reflects the historical burden of the x86 architecture. Over the past 40 years, x86 has accumulated severe historical bloat.
Because of backward compatibility.
Exactly. Its dominant market position requires strict backward compatibility. A modern x86 processor still physically contains the hardware logic to execute legacy instructions designed in the 1970s.
That's incredible to think about.
It is. During a standard boot sequence, a modern processor must literally cycle through its own evolutionary history. It activates in 16-bit mode, transitions into 32-bit mode, and finally engages its 64-bit capabilities. Housing all this obsolete logic requires vast amounts of physical silicon space and drastically increases heat generation.
And the RISC philosophy emerged as a direct mathematical response to that bloat. Computer scientists Patterson and Hennessy utilized strict quantitative analysis to prove that complex instructions were almost never actually used by compiled software.
Right, they were just taking up space.
So by removing the complex instructions entirely, architects could simplify the silicon layout. This allowed the remaining basic instructions to execute at vastly higher clock speeds using those aggressive pipelining techniques we discussed earlier.
And this optimized RISC philosophy is the foundation of the modern RISC-V architecture, which currently dominates the market for mobile phones, tablets, and low-power smart devices.
And the need for extreme optimization is paramount right now because the industry has reached a physical boundary. For decades, computer architecture relied on Moore's law, consistently doubling transistor density and increasing clock frequencies.
But we can no longer simply increase processor clock speeds without generating temperatures that physically melt the silicon.
Right, the heat wall.
Exactly. Therefore, architects have shifted their focus toward parallel architectures. If we cannot make a single execution pipeline run faster, we just have to run multiple pipelines simultaneously.
And this parallel processing takes two primary forms in modern hardware. The first is single instruction, multiple data, or SIMD. This architecture is the foundation of graphics processing units, GPUs.
Right. A GPU applies one single mathematical instruction to thousands of distinct data points at the exact same moment.
Which is highly effective for rendering visual pixels or processing the massive matrices required for artificial intelligence models.
Very much so. And the second form is multiple instruction, multiple data, or MIMD. This architecture defines modern cloud computing. In a cloud server, dozens of independent processor cores run entirely different software programs on entirely different data sets simultaneously.
But managing that parallel complexity requires a highly sophisticated operating system, doesn't it?
Yeah.
The hardware provides the physical resources, but the operating system provides the logical control.
Yeah, it utilizes a concept called concurrency to create the illusion that hundreds of user applications are running at the exact same time. It achieves this by rapidly switching the processor's attention between programs in fractions of a millisecond.
And to ensure stability, the operating system enforces virtual memory. It assigns each program a fake, isolated memory map, preventing one application from accidentally writing data into the physical memory space occupied by another application.
Which is crucial for security. However, these complex management systems and advanced architectural features can create severe vulnerabilities. We previously discussed out-of-order execution.
Right, where the processor guesses which path the program will take and begins calculating ahead of time.
Exactly. If the processor guesses incorrectly, it simply throws the speculative calculation away and resets. Unfortunately, the physical cache retains microscopic traces of that discarded data.
Ah,
Yeah. Malicious software can monitor the precise timing of how fast the cache responds to deduce what that discarded data was.
wow. And this physical hardware flaw is the underlying mechanism behind the catastrophic meltdown and Spectre security vulnerabilities,
Yeah,
right?
sadly, yes. It proves that architectural optimization can directly compromise system security.
And securing these systems is critical as we reach the atomic limits of silicon manufacturing. I mean, transistors are now so small that individual electrons can unpredictably jump across boundaries due to quantum tunneling.
Yeah, physics is literally getting in the way. Therefore, the future of computer architecture must transcend traditional silicon logic. We are currently observing a transition toward open source hardware tooling. Frameworks like Chisel and Broom allow smaller organizations to design custom architectures, breaking the monopoly of massive semiconductor corporations.
But beyond silicon entirely, researchers are developing completely novel paradigms, like optical computing replaces electrons with photons, utilizing the properties of light to process information with zero electrical resistance.
It is mind-blowing.
And DNA computing leverages synthetic biology, encoding massive archives of digital data directly into the complex molecular structure of DNA strands.
Not to mention neuromorphic engineering, which abandons traditional logic gates entirely. It attempts to physically manufacture the microscopic cortical columns of the human brain.
Designing chips that process signals through biological patterns rather than binary mathematics.
Yeah. And finally, we must acknowledge the paradigm shift of quantum computing. A traditional architecture is strictly bound to the binary states of 0 and 1. But a quantum architecture relies on qubits.
Right. The code.
By utilizing the quantum mechanical property of superposition, a qubit can exist as a complex probability, representing a 0, a 1, or any proportional state between them simultaneously.
So it's not just on or off anymore.
Exactly. This allows a quantum processor to evaluate millions of probable realities at the same time, solving complex cryptographic or chemical problems that would take a traditional silicon architecture thousands of years to complete.
It's just staggering to think about. We have traced the evolution of computation from the physical gears of the 19th century to the probabilistic states of subatomic particles. And as we wrap up this comprehensive analysis, I want to leave you, the listener, with a final concept to consider.
It's a profound thought.
We have spent decades mastering the highly predictable, deterministic logic gates of silicon. As we transition into biological neural networks that grow and adapt, or quantum systems that operate on pure probability, will we fundamentally lose the ability to write exact, line-by-line assembly code.
Right, if a machine learns rather than executes.
Could the future of computer architecture become a black box? Totally incomprehensible, even to the very engineers who design it. It's something to really mull over. We strongly recommend that you read the actual book, Computer Architecture, From the Stone Age to the Quantum Age by Charles Fox, to study these profound structural concepts in much greater depth.
Highly recommended.
Thank you for listening, friends of the show. We highly encourage you to subscribe to the program to receive our future detailed technical reviews. We wish you a great day.